Hello, yes, my name is Lawan Joski, and here I will talk to you about the equimolar counter-diffusion. To elaborate that, we have here I will go based on this graph. I will tell you about, we have two tank A, tank 1 and tank 2. In tank A, we have a species A, in tank 2, we have species B with different concentration. So in tank A, the concentration of A is higher. Here we have concentration of A here, and then we have another concentration of A in tank 2, but the concentration of A in tank 2 is lower than the concentration of A in tank 1. The concentration of B in tank 2 is higher than the concentration of B in tank 1. So we can now, and they're both separated by a valve here. And when you take the valve off, we can say that the species A would diffuse from the highest concentration to the lowest concentration, which is in tank B. And the species, like, it would go that way, right? And the species B would diffuse from the lowest for the highest concentration in tank B, in tank 2, to the lowest concentration in tank 1. And so that would bring us to tell that there is a equimolar counter diffusion, which is noted here. You can see right here that the net molar flux of A is equal to negative net molar flux of B, and this is what we call the equimolar counter diffusion. And we take that apart and we resolve the net molar flux of A. Right here we'll show you the calculation, which is NA, the net molar flux of A, is equal to negative concentration times divisibility A from A to B times the change of mole of A over the change of distance plus the mole fraction of A times the net flux. And we can say here that the net flux total is equal to net molar flux of A plus the net molar flux of B, and that will give us 0. And if you see here, right there, you can see that when you bring that here, you have Na plus Nb that equals 0. And we also know that the net molar flux of A is equal to the diffuse of flux of A, noted here as Ja, and the net molar flux of B is equal to the diffuse of flux of B, noted here as Jb. And now, based on the Fick law, we have the net molar flux of A is equal to negative concentration times diffusibility of from A to B times the change of mole of A over the change of distance right here. And this is an equimolar counter diffusion in the steady state. So now you can see that on the graph right here. If you're trying to graph that from the mole fraction based on distance, you can see here that the mole fraction here on Z1, from Z1 it decrease, going towards Z2. So there's a diffusion of species A from Z1 going towards Z2, which is from the higher concentration of A to the lowest concentration of A. And we have also here for the curve XB, we have a diffusion of species XB from the highest concentration, which is in tank 2. So from Z2 going towards the lowest concentration of species B, which is towards Z1. And then here we can note that the net molar flux of A is equal to negative molar flux of B. and the diffusibility from A to B is equal to negative diffusibility from B to A. So we have it right here. This is it. Thank you very much.
What's next?
Next, we'll give the word to Mr. J to explain to you the following. Finish it with the rest. Thank